Okay. So I would like to thank Kenji for this extra time he gave us. Okay, if some of you would like to start with the question to Kenji.
Well, if I may, I will start with a question.
Yes, of course. Please, Ivan.
Which is still on what actually Christian was asking before during at the end of your lecture, Professor Takizawa, which is you discussed the effect of the let's say outlet stabilization put on the inlet. And this is actually an approach that is shared by many other people to use this very same stabilization. And you would say that you're instead introducing the constraint on the profile as you do has let's say an improved effect in terms of stabilizing effect, or still there may be some stabilization on pressure that has to be considered.
Okay, so we don't need to any stabilization. So the idea is just having one single unknown which is constrained by incompressibility constraint. So that is the idea. Once you determine the flow rate, it determines the profile which resulted in the energy, what energy is coming into the domain. So that is stable, that's for sure. So that is our direction. And having outflow stabilization in inlet is having very different pressure compared to actual traction. So that doesn't seem to be good. You need to push a lot, otherwise you cannot get into the flow. That is what we think.
Okay, so basically you're not just prescribing the profile of the velocity, but also the intensity.
No, that is determined from overall system.
Ah, okay. Okay, see. Okay, thank you very much.
Cristobal, please.
Yeah, so but I wanted to ask the same, but it's not clear to me how do you actually, because you're imposing a pressure boundary condition. I mean, maybe you just answered to Ivan, but I didn't understand it. How you actually impose the flow rate? Because you're imposing, you have only one inlet and one outlet, and you're imposing a pressure, so you don't have no control on the flow rate, or are you doing it another way, or?
So flow rate is basically overall damping inside of a system. So it will be determined by that. If you have higher velocity, then you will have more energy dissipation. So from that, the right flow rate will be determined automatically.
Okay, I don't see how that could be. I understand that you increase the velocity, you increase the dissipation, but it doesn't mean that you have a priori control on the energy inflow, on this spurious energy that is coming to the convection. So, well, maybe
based on our system, once you determine, so basically, how much energy into the domain depends on only flow rate.
Yeah, because you constrain the shape. I understand.
Right. Yes. Therefore, flow rate and energy is already kind of set. So based on flow rate, how much energy dissipate will depend on inside of the domain, and that should be equal to what you impose. So
no, when you write the energy balance of the problem, I understand that you constrained and only the flow rate appears, but the flow rate is an unknown. So you don't have an energy, energy stable problem a priori. If you will know the flow rate exactly like you will be giving it, yes, but in your case it's not. So I understand that when the more information you give to the problem, the less tendency it has to blow up, but it doesn't mean that you will always work. So I imagine that you increase at some point the pressure more. So at some point the convective energy on the boundary that will enter to the domain will just make everything go up again. It will just take longer than without putting anything or without constraining. But I don't see how you can know the flow rate if you're imposing pressure boundary conditions.
So
you just don't know it. It's an unknown of the problem. From what I know. I don't know what the others think. Maybe.
Like a pipe. So if you have a higher velocity, energy dissipation becomes higher. So, right?
Yeah, but also the incoming energy. So they have a spurious, you have that term that you actually want to cancel with the other stabilization. That term also becomes larger. So it may be that you have more energy. It could happen that you have more energy dissipation than what actually is entering because you constrain. But it doesn't mean that a priori you have the right energy balance. I mean, I don't know if maybe I see it wrongly, but.
Well, mathematically, I understand what you said, but like in an engineering point of view, that is kind of, to me, it is obvious. So if you put the traction boundary condition, what is the velocity, what is the speed you can get is physically determined, and we have that condition. So to me, it is clear.
Okay, I still don't see how. I mean, but yeah, maybe it's a matter of a longer discussion.
Let me explain something similar situation. If you want to expand the balloon becomes bigger, and same pressure, you are getting larger force. Then you can say you don't know how much it becomes bigger, right?
Yeah, but in physical experience, you don't have this problem because everything is a continuous. So you don't have a spurious energy due to the convection that is entering to the domain they don't know. So it's a problem of the model. It's not a problem of the experimental setup. So you will never have that experimentally. So I don't see. So when you use the other type of boundary condition where you stabilize with the negative part of u dot n, like you showed before, the constraint, yeah, then you get an energy stable system and you shouldn't blow up. But because you are really, when you write the energy balance, you're canceling out the spurious energy, the convective energy boundary. But when you just constrain, I think, okay, you reduce the options of the flow to do stuff, but still you don't know, there is no a priori, you're not giving a priori the flow rate, so you still, it could happen that it blows up if your pressure is large enough. So you can maybe try it, I guess. So even for without a valve, it's just a tube and you do that. Well, that's no, with a tube it could work because you just, yeah, it could be that it blows up or not because if you have a, no, it could be. If it's dynamic, it's a dynamic problem because your parabolic profile is not compatible with a warmer state solution. But yeah,
well, I guess the energy into the system is pressure and velocity part, but velocity part is like just based on velocity magnitude. So maximum velocity magnitude is already determined. Then you can have an upper limit based on flow rate. So it is not completely free. Traction, you have freedom, but we are constraining traction. So I think that my view is it is a physically right condition, and as long as the velocity profile is as what we design, we know that there is a solution. So I'm not talking about mathematics, but that is my understanding. So probably there is a way to prove maybe in math.
Okay, very, very interesting discussion, and I hope that this could be the opportunity for interaction. If Cristobal has no other question, I know that there is a question from Lorenzo Bennati, please.
Okay, yes. Hi, Professor Takizawa, and thank you for your very interesting conference. I have a question regarding the imaging. Regarding the ventricle, the reconstruction of the ventricle, which method do you use to reconstruct the ventricle? MRI or other kind of method?
So we used a CT image actually, but that was only I mean one timing, and then this we determined using structural mechanics. So it is we couldn't get we don't have a good collaborator actually in the medical field people. I mean, I have many friends, but they don't have a good resolution pictures, so we kind of made it up.
Okay. Okay, thank you.
Other questions? If not, I have a curiosity for Kenji. What about the aortic root? The movement and the interaction between fluid, blood, and the aortic root is considered? If yes, with the same method, space-time as for valve, or is at the moment fixed? What about this?
You mean which case?
The aortic root. Yeah, the aortic root, I do not understand if is it rigid, okay, or if there is the interaction with blood, and if yes, if you use the same technique used for the valve, so the space-time method, okay, also for this, or for aortic root, you use the standard ALE, I don't know.
So that was originally the FSI was based on immersed boundary method together with UV and Ming Chen. And after that, basically we extracted the motion. So it is a fluid mechanics only, but moving boundary.
Okay, so you are accounting for the interaction with the aortic root with the same in the same framework. You have only one framework for both the interactions, valve and aortic root. Is it true?
Yes. Yes.
Okay. Okay. And what about, maybe you have mentioned this, but I don't catch it. I did not catch it. What about the Reynolds numbers? Are you able to perform your simulation with physiological Reynolds numbers, or still, or maybe with reduced, and you are working on this?
Okay, so we never thought it is necessary to reduce, especially for arteries. it is pretty low for us. For example, we are using regular, like a parachute computation or other kind of much higher Reynolds number. So they are pretty low.
Okay, so you are working on making your strategy more robust from this point of view. Okay, thank you. Alberto, please.
Thank you, Professor Takizawa, for your talk.
Alberto Zingaro, sorry, just to Lorenzo Bennatti and Alberto Zingaro are a PhD student at Politecnico in our group. Please, sorry.
Yeah, I just have a curiosity. So you mentioned that you're using an indicator, so the oscillatory shear index, but defined in moving domain, right? Maybe I'm wrong. So if you could like spend a few words on this, like if you can give us more specifics on how you define the OCI on moving domains, like in your case in the moving valve, for example.
Yeah, we wrote clearly in the paper, so maybe you can find from our website. But the idea is very, very simple. So what we want to know is the wall shear stress with respect to a surface. That is, I think, people want to know, which means even it is moving, we move the wall shear stress vector. So we map into like a reference configuration always. Then the wall shear stress is with respect to the reference frame. And once you move to the reference frame, you can just do regular OSI calculation.
Okay. Okay. So, okay. Yeah. It's clear. Okay. Thank you very much.
Okay. Other questions for Professor Takizawa? Okay. If